When I was younger, I was obsessed with this beautiful thing. I kind of still is now. This beautiful thing, not this painting, called the Fun Times Primes table in the wonderful world of primes. When it comes to primes, I'm the one who has time to sing along if you're able. Fun times with the primes table. Yeah, I just like finding a listing prime. When I was young, I had a misunderstanding about this table. Anyway, you see all these rows? There's only one in the prime in the 2 column, and that's 2 itself. There's 1 prime in the 5 column, 5 itself, because they're both factors of 10, which is the base. So obviously 12, 22, and 50 and 25, they're all going to be multiples. They're all going to be multiples of 2 and 5 respectively. And of course 4, 6, 8, 8, 0, these columns doesn't even exist here. Other columns. That's what it comes up. You see, in 1 row, the 1 enders, the 3 enders, the 7 enders, and the 9 enders. We have all these rows, and they seem to all go on forever. All these rows seem to continue. And if you look at it from grayscale, they all seem to have the same number of, numbers, prime numbers. That is temporal. See, the 3s have temporarily taken the lead with all this way. It goes up to 120 or something. But when you expand this to 1,000 or something on a greater scale, they're most likely going to be equal. They're like very close ratios. When I was younger, I had a misunderstanding that primes ending in 1, primes ending in 1 or 7, the 1 enders and 7 enders, they have a greater chance of appearing than and primes ending in 3 or 9. Well, I have reasons for my understandings. My misunderstandings mainly because I thought that these numbers 51, 57, and 87, 91, and 111, 117, 119. I thought these were prime. They're not. Not prime. Definitely not prime. They're definitely not prime. Not prime. Not prime. Not prime. Not prime. They're all composite. Well, eventually, I grew a little older. I learned the divisibility test for 3. So the divisibility test for 3 is you add all the digits up and see if it's a multiple of 3. Well, 5 plus 1 is definitely 6. So goodbye. 5 plus 7 is 12, which is definitely multiple of 3. Goodbye to you. 3 plus 7 is 15. And 1 plus 1 plus 1 is 3. Bye. 1 plus 1 plus 7 is 9. Bye to you. But these two pass the test, which means they're not divisible by 3. So they're actually still on my list. It is. When speaking of the divisibility test for 3, I'm going to give a short explanation on why it works. Suppose we have the 4-digit number A, B, C, D. There's not A times C times D. It's literally A on the thousands place, B on the hundreds place, C on the tens place, and D on the ones place. There, simple as that. Now, if we have A plus D, B plus C plus D, let's say this is a multiple of 3. Now, according to the Pseudoprimes property of multiplication, a multiple of 3, plus a multiple of 3 is still a multiple of 3. So we can add on a multiple of 3 and still get a multiple of 3. Let's say we add like 999 A's and 99 B's and 9 C's. What did that give us? That's right, 1,000 A's and 100 B's and 10 C's and D, which is basically equal to a 4-digit number A, B, C, D. This is a multiple of 3, and since this has 999,999, these are all multiple of 3, so this is multiple of 3, they add up to a multiple of 3, this is going to be a multiple of 3. There. That's why this thing works. But for the other numbers, it's not that easy. As you can see, 91, 91, and 119, they're still on my list. Actually, my oldest is to I put this on Discord server. And then there was that dude who was like, hold up. What? No, it's Prime! He didn't actually say it in all caps, but he just took out his factor calculator and it said 91 is equal to 7 times 13. Which is unfortunate because unlike 3, these numbers, they don't have easy divisibility tests. No divisibility test, at least no easy ones, so you just have to do it the hard way. Or just traditional division. Yeah. No. Most people don't even realize that at 9 was prime. Well, most people in the number box community realize it though, because 91 is something called a triangular number. Which is numbers that can be formed in a triangular shape, like this, like so 1 plus 2 plus 3 plus 4, and so on until you stop at point. And the total sum is going to be a triangular number. Well, when designing number box, triangular numbers should have this thing called a step mask. So, of course, people design number box will definitely memorize all of these triangular numbers, and they know that 91 is a triangular number. Specifically, it's 1 plus 2, 2 plus 3, all the way up to 13, 91. And prime numbers can't be prime numbers. Besides 3, 3 is the prime number, 3 is the odd one out. The others are not prime. So, yeah. Oh, and then 119 I talked about, that's 7 times 17. Yeah, 17 doesn't have an easy divisibility test either. So yeah, we can basically call these numbers that look like primes that are actually composites. 91, 119, we can actually call them pseudoprimes, which means they're fake primes. They're imposters. Well, technically, the only pseudoprime under 100 is 91. Most people only do decide prime numbers up to 100. They usually don't try to go over 100. So I guess 91 is like the 9 number for them. It's higher than number 9. Higher than naughty number 9. Yeah, I think we need to change the song. Naughty number 91. Yeah. So next on the list. This is 7 times 13. This is 7 times 17. And you may expect the next one to be 7 times 90. And boom, you're correct. 7 times 90, 133. Well, people can actually get away with the 19 divisibility test, but literal, there's no, almost nobody knows the 19 divisibility test, so I'm gonna count 133. Of course, we can do this pattern with 7 times 23. That's gonna be 161. 7 times 29 is 203. As there are. We can't count the multiples of 11 because 11 actually has an easy divisibility test. So basically, you add the first, minus the second, add the third, minus the fourth, add the fifth, or basically just add up the odds, add up the evens, then take the difference of those and see if it's a multiple of 11. I'm not going to explain deeply here. So obviously, 13 times 13 is going to be a pseudoprime. It's 169. Unless you memorize all the prime numbers, all the square numbers, come on. It's 13 times 13, 14 times 14, 15 times 15. If you memorize all that, it would not be a pseudoprime for you. Of course, there's 13 times 17. It's going to be equal to, like, hold up. 3 plus 7 is 10, 121. This is 221, I think. And there's 13 times 19, which is going to be equal to, alright, 3 times, alright, let's see, 3 plus 9 is 12, 3 times 9 is 27, and what's this, 1 times 1 is obviously 1. Alright, so 247. Yeah, I think so. We have a whole bunch of pseudoprimes here. And the interesting thing is, a lot of these numbers don't really pass that many prime tests. The composite tests. Actually, they have some other prime tests. So unless you deliberately go testing their factors, they're going to appear as an extremely innocent prime. Yeah, look at that innocent face. Yeah, come on. It's innocent. Innocent, I say. Look at the innocent face. Innocent. Definitely innocent. 9-1 is innocent. Innocent. Not sure though. 9-1 is the 9 number. As I said. Well, we've been talking about these pseudoprimes. What's so interesting about them anyway? Well, we can use them to test if prime tests actually work properly. Yeah, I think basically the only thing we need to primes for, but is next time if someone asks you if some number is prime or not, you must remember to test it by every prime up to its square root. Hold up, why square root? Well, if it's a composite number, let's say it's 247, which is a composite number, is 13 times 19. Now, we don't know it's 13 and 19 yet, but if it's going to be a composite number, it can be written as A times B. Now let's say we tested a number bigger than square root. 8 times. Let's say a is bigger than the square root of 247. Then we can divide this whole thing, and we'll get divide this by this, we get this is greater than and of course we can flip it over. Remember to flip the sign as well. Okay. One of the pains of Christmas is to not flip the sign. You must flip the sign. So B is gonna Oh wait. We're dividing by this, so the A's have been cancelled out. We shouldn't write the A here. This is 1. The A's have been cancelled out. There's no A here. Definitely no A. We get B is smaller than 247. And since we're testing this in order, we're testing first 2, then 3, then 8, then 5, then 7. And so we would have tested B first. We would have tested B before A, or tested B before A. So we don't even need to test A because when we test B, then we already know it's a composite. We don't even need to test A. We don't even care about A anymore. Or maybe B is a composite. Then that's great because then B would be the prime smaller than B. They're both smaller than B, so we haven't tested them. So yeah, we only have to test the prime smaller than the square root of 247. Since the biggest square number that's smaller than 247 is like 225, which is 15 squared, we only need to test the prime numbers smaller than 15. Smaller or equal to 15. But of course, 15 isn't primeless, so it's 2, 3, 5, 7, 11, 13. Let's see, 2, nope. 3, nope. 5, nope. 7, nope. 11, nope. 13, oh! Yeah! It's 17 is 13 times 19. 13, yeah. So I guess that's basically it for a video. Why am I returning to this extremely bad drawing? Anyways, this bad drawing says goodbye. So, yeah, goodbye.